we're in the middle of March. I just made my own calendar.
And it's madness.
I do know it's March Madness time. But we should probably just check those scores in between classes and focus on this fabulous mathematics we have coming up this unit. So, if we look at this, it's a math modeling unit. And for us, that means we're going to go back and fill in all our gaps with our functions. We're going to grab some good ones. We're going to start off today with some square root and cube root functions. Tomorrow we're going to look at some step functions. There's a lot of real-world application that can occur with step functions. We're going to look at some of that. We're also going to do some graphing, rounding up and rounding down functions. Then next week we're going to look at piecewise. And then we'll finish this off with some absolute value functions. And apparently you're going to have homework out of a boo next week. All right? And then we have a review and we have a quiz. And then we're going to kind of compact it a little bit because I don't want to wait till after spring break to test you. So the test won't be as long. And I'll make sure we can finish it in one class period. And we'll have that on April Fool's Day, except it's no joke. Okay? So then we're going to finish up with odd and even symmetry. And
That's my dad's birthday.
oh, that's hilarious. Wow, okay, so apparently we're going to celebrate the birth of many, many people this day while we ace our test. Alright, so that's what's coming up for us. Now, there's going to be a lot of in and out, thanks to spring sports, which I love them. Sports are awesome. No, I really do enjoy sports. I do know that some of you are in a crunch. So what I did was, which is normally not what I do, I left up last year's calendar. So obviously the dates are different because it's 2015, and I don't give the exact same assignments. But if you're going to be out and you know ahead of time, you might want to see. Last year I did test after the break. That was
How'd they do?
cruel and unusual punishment. But this year we're gonna do it before. So if you need to go maybe watch a YouTube on it ahead of time if you're going to be out or something, you might want to do that. I left it up there for you because of the craziness of this time of the year. All right. So today I said we're going to look at two very interesting functions. We're going to start with root functions, square root and cubed root today. Now, all of these functions are going to be basically in our same old vortex form, where we're doing our shifting and our stretching and our compressing and our reflecting. So once we know our moves, we're good, because everything else works the same way, as it always has, as it did for the quadratic, as it did with the exponential, as it did with the logarithmic. We shift things around and we apply the moves. So, what kind of moves do you think we'd be doing with a square root function? If we think about the parent graph, the parent graph is just y equals the square root of x. It has nothing extra. It's not shifted, it's not reflected, it's not stretched, it's not compressed. There's nothing extra. Y equals the square root of x. That's our parent graph. So what kinds of numbers would we want to plug in for x?
Positive.
Positive. Positive squares. Like 1. What is the square root of 1? 1. What's the next number I'd want to try? 4. The square root of 4 is 2. What's the next number I would want to try? 9. Because the square root of 9 is 3. Okay? So, really nothing new except different moves. So if I were to go graph the parent, y equals the square root of x, I'd start at the origin, and then I'd go right 1 up 1, and plot my point, and then right 1, 2, 3, 4, and up 2, and plot my point, and then draw in the square root. Okay, so now that I made that ugly, I'm going to get rid of it. So we can take a look at the domain and the range of this function. Of the parent graph, can x be any old number? No, because we're not going to be able to graph a square root of -4. That's imaginary, right? So the domain is restricted. It goes from what? 0 to positive infinity. That's what the domain of this function looks like. Now with the parent graph, the range also goes from 0 to positive infinity. All right, so we have 4 little examples here. We could also talk about other things. Increasing, decreasing. This entire function is increasing from left to right. So it increases from 0 to positive infinity. It doesn't decrease anywhere. We could also look at x and y intercepts. Now, in behavior, this only has one end that's continuous. It goes on forever. So if we were to describe the end behavior, we're really only describing this end that continues. So as x approaches positive infinity, y also approaches positive infinity. Okay, so let's look at this square root function. There are transformations that have occurred to this parent graph. Where has that starting point shifted? Left 3 and up 1. Now, the moves from that starting point are the same though. The square root of 1 is 1. The square root of 4 is 2. That makes sense?
Yes. I'm used to graphing these continuously. I'm like stopping at a point.
This one, it starts. It starts right there. It's not continuous in both directions. All right, number 2. Where will we start the next graph? Up 4. 1, 2, 3, 4. Now, this is negative. A negative reflects it over the x-axis, which causes our y's to change to the opposite. It also has the 2 there. So not only do they change to the opposite, they all get doubled. Right? So instead of going over 1 up 1, we go over 1 and down 2. Instead of over 4 and up 2, we go over 4 and down 4. And so our graph goes down. So if we're thinking about our domain, what do the x values look like for this function?
Negative.
The x values start here at 0 and go forever right. But the y values are a little different. Bottom to top, it goes down forever. So negative infinity to what is the top y value? What is the greatest possible y value? Positive 4. Least to greatest. What are the possible y values? Least to greatest. All right, number 3 is kind of cool. Because number 3 not only has a reflection, but it's one we haven't done in a while. The negative is inside with the x, isn't it? And to properly work this problem, we have to factor out any coefficient for our x. We haven't done a ton of practicing this, but we're going to pick it up in this unit because it will be important for what you do in trig and pre-calculus. You'll always need to factor out any coefficient of your x. So we're going to pull that back. You see how it's in the next one too?
Yes.
We're going to take a look at that a little more with these functions. So here we have a negative. Well, we know from the one we just did, if the negative is, whoops, try to go back to pink. If the negative is out in front, it causes a reflection over the x-axis like this. But the negative inside with the x will cause a reflection over the y. So this is what it's going to look like if the negative is in here. So let's see. First, we're going to plot what we know from transformations. Then we're going to go back and make sure that makes sense. So where is the starting point? It would be positive 2, because the opposite of this was x minus 2. So positive 2, negative 1. All right. Does that make sense?
Yeah.
If we plugged in positive 2, it becomes negative 2 plus 2 is 0. And 0 minus 1 is negative 1. Yeah. Now, because this is negative, let's think about what this does to our moves. It changes the x's to the opposite. So I would go left 1 and up 1. Left 1, 2, 3, 4, and up 2. Okay, so let's test it. If I plugged in an x value of 1, if I plugged in a 1, what is negative 1 plus 2?
1.
1. What's the square root of 1?
1.
And 1 minus 1 is 0. Is that point at 1, 0? Yes, it is. Now this one's a cool one. If I plugged in negative 2, it becomes the opposite of negative 2, which is positive 2. And 2 plus 2 is 4. The square root of 4 is 2, and 2 minus 1 is 1. If I plug in negative 2, do you see I get out 1?
Yes.
Okay. So those transformations work. It gives you those points. So you don't have to worry about picking the correct x values. That's a lot harder. Okay, now this one has a bunch of stuff going on with it. This one has this negative 3 out in front, so it's going to go down and be stretched vertically. So it's going to be like this, right? Okay, plus it's got a 2 in here. So we know we need to factor that out. So let's start dealing with that now. Y equals negative 3 times the square root of, got to factor that 2 out, and it leaves me x minus 2 plus 5. So where does this start? Where's my starting point for the square root function?
2, 5.
The opposite of this, so it's going to be 2, 5. 2, 5. All right, let's get back to my moves. We got a couple things going on here. We got this negative 3 right here. So each one of these has to get multiplied by negative 3. We also have a 2 in here with the x. Remember, when it affects the x, we always do the opposite. So what is the opposite of multiplying the x by 2? Dividing the x by 2. So what do the moves look like for this one? 1/2, negative 3. 4 divided by 2 is 2, negative 6. 4.5, negative 9. That's what the moves look like for this function. So we go over 1/2, down 3. Over 2, down 6. Over 4.5, down 9. And it goes like that. Okay, so square root's either going this way, or that way, or that way, or if we had a double negative, it would be down that way, wouldn't it? Okay, so those are our options for square root. Now, let's take a look at another root, the cubed root. Now, when we look at the cubed root, this part looks a little square rootish, but then we have this part over here. And the reason we have this part over here is because now we're taking an odd root. And can we take an odd root of a negative number?
Yes, you can.
Yes, that's why we get this part.
Because math.
Okay, because math. All right, so now let's think about our moves. The parent graph would be y equals the cubed root of x. So we got nothing extra with the parent graph. So we want to pick values for x that we can take a cubed root of. So we're going to go with our perfect cubes. Like negative 8. What's the cubed root of negative 8? Negative 2. What about negative 1? What's the cubed root of negative 1? Negative 1. What about the cubed root of positive 1?
1.
1, and the cubed root of positive 8 is 2. So those are numbers that we would try. Now, if we tried other numbers like cube root, next cube root would be 27, right? Little large there. Okay, so we can take a cube root of anything, can't we? A positive number or a negative number. So our domain is not restricted. And we can get out pretty much anything. So our range is also not restricted. All right, now this has more of an inflection point right here. This is where I'm going to start, but I can call that an inflection point. Do you see how this goes from concave up to concave down right there? There's an inflection in the graph right there. And that's where I'm going to start. This is the point that I'm shifting around, that inflection point. So on example 1, where does the inflection point shift to?
2, 1.
2, 1. Right 2, up 1. And then I have to think, what are those numbers I can take cubed roots of? Negative 8. So if I went left 8, I would go down 2. Negative 1, left 1, down 1. Positive 1, right 1, up 1. And that's all that's going to fit on my graph this time. But I do want to make it look like it has that inflection. Right here. All right, now, do you see that this entire function is increasing from left to right also? Number 2, how is that inflection shifted?
Down 3.
Down 3. But this time there's a 2 out in front. If the 2 is out in front of the entire function, we multiply those y's by 2. Not much is going to fit on here. I'm going to go off a little bit. Off 8. And then instead of 2, it's actually going to be 4. We have vertically stretched this function. It's like it's been pulled vertically. Okay, mine looks terrible. I hope yours looks better. I don't have much of a curve right there. There we go. Phew! Second try was much better than first. All right, number 3. How is this one shifted?
Down 4. Left 4.
Left 4. Left 4. Now, it's got a 1/2 out in front. If it's out in front, it affects the y's. So this is going to cause a vertical compression by a factor of 1/2. It's going to make it skinnier than it was to start with. So if I go over 1, I go up 1/2. If I go over 8, I go up 1 instead of 2. So this got vertically squashed. Or vertically compressed by a factor of 1/2. Now this is kind of cool. This has a negative out in front. A negative out in front is going to cause a reflection over the x, correct?
Yes.
But what if the negative were inside? It would look identical, wouldn't it?
Yes.
Because whether I change my x's to the opposite, or whether I change my y's to the opposite, both changes have the same effect on the graph. Okay. So, where is this one shifted?
Up 2 and left 1. Up 1 and up 2.
Up 2, left 1, left 1, up 2. Either way. Either way, that's the same spot. Left 1 and up 2. Up 2, left 1. All right. Now, instead of going right and up, though, we're going to go right and down. 8 and down. Left and up. And that was caused by that reflection over the x-axis, which doesn't look any different than the reflection over the y-axis for this function. Okay.
Homework?
It is your lucky day.
No homework?
It shouldn't be, because you should finish this before the bell. Now, here's the homework. You're going to graph all 1 through 12. It says give the characteristics for all, but I only want you to give the characteristics for the evens. And if you work diligently, you should finish before the bell rings. That was an if, because I saw you pick up your phone.
Who sits here before me? Is that